Niacin's reputation as a simple B vitamin or cholesterol-lowering agent has long obscured one of its most intriguing properties: its role as a direct agonist of the G-protein-coupled receptor GPR109A, also known as HCR2. Unlike NR or NMN, which do not interact with this receptor, niacin can activate GPR109A at micromolar concentrations achieved even with modest doses. This interaction initiates a cascade of signaling events profoundly influencing inflammation, gut barrier function, and metabolic homeostasis, all separate from NAD synthesis. GPR109A is expressed in a surprising range of tissues, including adipocytes, intestinal epithelial cells, colonic immune cells, macrophages, dendritic cells, and microglia in the brain. Its activation by niacin leads to decreased intracellular cyclic AMP in adipocytes, explaining niacin's inhibition of lipolysis and its lipid-lowering properties. But beyond adipose tissue, GPR109A activation exerts potent anti-inflammatory effects by suppressing NF-B signaling and inhibiting pro-inflammatory cytokines such as TNF-A, IL-6, and IL-1 set in immune cells. In the gut, GPR109's anti-inflammatory role is especially compelling. Butyrate, a short-chain fatty acid produced by healthy gut microbiota, is an endogenous ligand for GPR109A, which partly explains why fiber fermentation and a butyrate-rich microbiome protect against inflammatory bowel disease, IBD, and colorectal cancer. Niacin can mimic this protective effect by directly activating GPR109A on colon epithelial cells and resident immune cells, leading to reduced gut inflammation, improved epithelial barrier integrity, and increased production of anti-inflammatory cytokines like IL-10. Animal models of colitis have demonstrated that oral niacin can decrease disease severity, reduce histological damage, and shift immune responses toward regulatory phenotypes, largely via GPR109A. Benefits not reproduced by other NAD precursors. This GPR109A-driven modulation extends to systemic immunity. In macrophages and dendritic cells, niacin reduces the expression of MHC2 and co-stimulatory molecules, limiting excessive T-cell activation while favoring the development of regulatory T-cells, TREGs. This immunomodulatory effect suggests potential utility in autoimmune and inflammatory conditions beyond the gut, where a shift toward tolerance can reduce chronic tissue damage. In metabolic disease, chronic low-grade inflammation, especially in adipose tissue, is a driver of insulin resistance and metabolic syndrome. By activating GPR109A in adipose-resident macrophages, niacin suppresses inflammatory signaling pathways that would otherwise promote cytokine-induced insulin resistance. Some animal and early human studies show niacin reduces adipose inflammation markers independent of changes in NAD or lipid profiles, highlighting the therapeutic potential of GPR109 agonism for restoring insulin sensitivity. Moreover, GPR109 as expression in microglia points to possible neuroprotective roles. While less studied in humans, rodent models of neuroinflammation indicate that niacin or butyrate activation of GPR109A reduces pro-inflammatory microglial activation, suggesting a potential to dampen neuroinflammation implicated in Alzheimer's disease, Parkinson's, and multiple sclerosis. Crucially, these benefits are independent of niacin's NAD raising capacity. NR or NMN, despite raising NAD, more directly, do not activate GPR109A and therefore cannot replicate this direct anti-inflammatory mechanism. That makes niacin unique among NAD precursors. It offers dual pathways to health span benefits: systemic NAD restoration and receptor-mediated immunomodulation. This receptor-mediated action has profound implications for gut health. By mimicking butyrate's GPR109A activation, niacin could compensate for microbiome imbalances that reduce butyrate production, offering a nutritional strategy to maintain gut homeostasis even when dietary fiber intake or microbial diversity is suboptimal. It also suggests niacin could support therapies for IBD, leaky gut, or colorectal cancer prevention, especially in individuals with modern diets low in fermentable fibers. Furthermore, niacin's ability to shape immune responses away from chronic inflammation has relevance for metabolic diseases like obesity, type 2 diabetes, and possibly autoimmune conditions. By calming adipose and systemic inflammation, Niacin could improve insulin signaling and metabolic flexibility independently of or synergistically with its effects on lipid profiles or NAD. In summary, niacin's engagement of GPR109A represents a powerful, underappreciated anti-inflammatory mechanism that complements its better-known lipid and NAD boosting effects. Unlike NR or NMN, niacin's receptor-mediated action provides a unique opportunity to modulate gut health, regulate immune balance, and mitigate chronic metabolic inflammation, making it a more versatile therapeutic agent than its modern designer counterparts. Recognizing this pathway elevates niacin from a mere old vitamin to a sophisticated tool for addressing today's most pressing inflammatory and metabolic challenges.